Okay, wonderful. So, since Krishna was not there yesterday, we'll just do a 5 minutes quick recap of what we did. It will also help you guys, to just have a revisit to whatever we did yesterday. So, Krishna, bear with me if I'll just go a little fast, so that you know people also we have quite a bit to do today. So yesterday what we did is we learned basics of statistics. What is machine learning? I think you were in the Sundays class, so I think you probably I introduced a little bit of machine learning, supervised learning, and unsupervised learning definitions, and a little bit of linear regression also. So we did that in much detail yesterday, but I think you just had some idea from last Sunday's class. Okay, so we define statistics. What is the mean? What is the median? One important point to remember whenever you are, studying about mean and median. So I think yesterday we had a very good session about how an outlier is basically a data point which is not representative of the rest of the data. Something which lies beyond, is either it's a bad entry, either it's doesn't come from the same population that we are recording the data. For example, if you're recording the height and weight of Indians, suddenly an Australian comes and you record that height, and then again you continue recording height and weight for Indians. So that Australian height and weight will be an outlier to your data because he doesn't represent the same population for which your data is being collected. Okay, or it could be a bad entry. So most of the times, whenever the data is collected, some people might have a bad entry or mistakenly write something, and it will and hence it falls under uh, outliers. Okay, so what we define is a median is the middle value of the data arranged in a sorted order. It can be ascending or it can be descending. Okay, and a mean is basically the average of the values. Now, I think everyone answered this question correctly when we asked that which is a better metric when the data has outliers. So when you have outliers, your mean will be biased towards the outlier. So for example, in here, if you have 1, 2, 2, 3, 3, 4, 4, 5, and then suddenly you have a 200 or 1,000, your mean will move towards 1,000, right? But if your median has 1, 2, 2, 3, 3, 4, 4, 5, and 1,000, you're still the median will be 3, right? Because even if the 1,000 comes, your middle point will just shift by 1. It will not move towards 1,000. Okay, so this is a very important statistical concept that median is robust to outliers compared to mean. Okay, so this is very important. Just remember this. Okay, and okay. Okay, so moving on further, mode is not very important. Mode is basically the value which occurs most of the, occurs most number of times in the data set. So, for example, here 3 is occurring the most number of times. So basically, every data point you calculate the frequency of that data point in your data, and hence you say which has the highest frequency. That point you call as the mode. Not very important in actual real life applications, but it's good to know. Okay, so we calculate the mean, median. What is standard deviation? Standard deviation is basically the spread of the data. So how your data is spread or your data is varying about the mean. So I guess if you have any doubts on the calculation part, I'll just tell what is the calculations. For example, you calculate the mean and then you take the squared sums of each of the numbers from the mean. Okay, so for example, if your mean is here 3, then 1 minus 3 squared plus 2 minus 3 squared plus 2 minus 3 squared plus 3 minus 3 squared. Hence, like this, you add it up and then you divide it by the number of items. Okay, and that is called the variance. If you take the under root of that, we call it as the standard deviation. Okay, Hello, hello, hello. Hey, you guys can hear me now?
Yes, we are able. Yes, yeah.
Okay, okay. I think there was a problem in the connection. Okay, sorry about that. So we were so Krishna Kumar, just stop me if you have any doubts on the calculation of the variance. Uh, did you understand what we did here? Okay, that's great. Okay, so let's continue here. We have seen the variance. Okay, so we have seen the standard deviation. So just drop me a yes on the chat box if you guys can hear me properly. Okay, that's great. So what happens to the mean and the standard deviation when we add two? So for example, if you add an element 2, what will happen is your mean will change and your standard deviation will change because there's a new data point introduced. Okay, now when this is a very important concept whenever what happens to the mean and standard deviation when we multiply by 2. So when you multiply by 2, your mean and standard deviation both will change. Okay, so your mean will become twice and your standard deviation will be also twice. Okay, why it will happen? Just just imagine you are multiplying 2 to every element. Okay, so when you're calculating the mean, just you're just adding up divided by the number of items. Just take out 2 common from each of the items. Your previous mean was basically addition of this divided by 9, right? Now your 2 is out of the bracket. Whenever you are adding and you multiply by 2, your numerator will become twice, right? So we'll just end up in a mean which is twice of the previous one. And then similarly for standard deviation, you will have a mean twice. So this will be 6, this will be 2. So 2 minus 6 square plus 2 minus 6 square plus, sorry, 2 minus 6 square plus 4 minus 6 square plus 4 minus 6 square. So like this, you're adding up all the items. So you take out 2 common. Inside the square, it will be 2. When you're taking out from the square, it will be 4. So your variance will be 4 times. But whenever you're taking this, after you take the square root, it will again come back to twice. So just remember this, whenever you're multiplying the data by 2, your mean and standard deviation will be become twice of the original. Okay. Similarly, if you do divide by 2, it will become half of what was original. Okay. Now, this was just to explain that if you are shifting your data, if you shift your data, your mean will change. Okay, but your standard deviation won't change. Why? Because you are taking the differences, right? So even if this becomes 3, your mean will become more than, I mean, it will, this element will become 5, right? So 1 minus 5, so each of these elements will be shifted, so the whole data is being shifted, right? So just remember this, mean and standard deviation are not, mean is affected by the shift in the data. However, your standard deviation is not, because standard deviation is a difference in the data. It's the basically spread of data. Think like this, spread of the data will not change even if we are shifting the data. We are shifting all the elements, right? So the spread of the data will not change. It'll only increase the mean. Okay. So and if you're multiplying by each of the elements by 3, then your mean and standard deviation will become thrice. Okay, I guess there's no confusion on this. Normal distribution. Okay, so I think there was some little confusion on normal distribution yesterday also. Uh, what I had said that I'll add a handwritten note in the slide, but I couldn't get time yesterday, so probably we'll revisit this next week. Okay, and I'll do a handwritten note so that it is easier to explain. But for now, since we have a lot of things to cover today, I'll just do this very fast. So basically, a normal distribution is something which is symmetrical, which means the mean is equal to the median is equal to the mode. Okay, so symmetry about the center, and so 50% of the less values less than the mean exist below the mean, and 50% of the data greater than mean exist above the mean. Okay, because how do you see this? Because your mean is equal to the median, and median's definition itself is that it divides the data into 50-50 equal parts. Okay, so this is what is normal distribution. Normal distribution is typically bell curved like this. Okay, it will always be like this. And why it is called normal distribution? Because most of the things in your most of the distributions in your real life follow this normal distribution. Let it be the marks of the students, let it be the performance of employees in your organization, let it be the number of accidents happening in the road. Okay, so many will say a number of accidents happening in road is Poisson distribution, but then again Poisson distribution will approximate to a normal distribution at some point of time. Okay, so we'll not go into that depth right now, but just understand this. Okay, so heights of people, size of things produced by machines, errors in measurement, blood pressure, marks on test. Okay, Krishna, any doubts on this? I think this thing people have already understood yesterday. Do you have any doubts? Just drop me a yes or no here. I think I'm going a little fast. Okay, Krishna, that's great. No doubts. So why are we learning normal distribution? As I told that most of the things in your real life follow a normal distribution. Okay. So imagine this: when you are dropping sand from your hand, it will form into a heap. Okay. So that heap is also kind of a normal distribution. Majority of the particles will fall directly under your hand, but some will fall below, some will fall to the side. So distribution will be like a normal distribution. Okay. So this is very important. Your normal distribution, the mean is situated here, and these are one standard plus minus one standard deviation away from the mean. Okay, so if you go plus one standard deviation to the right and plus minus one standard deviation to the left from the mean, remember this is one standard deviation. So for example, if your average is 70 and your standard deviation, like we calculated the earlier time, is like it's a 5. So 70, 70, I'll write it here. This is 70 and this is 75. So this is 65. Imagine that you have conducted a maths test in your class, and you have plotted the test marks of all the students in the class, and the average is 70. Okay, now want to analyze the distribution of the marks in your class. So you say, for example, if your principal comes and says that what is the number of people or a number of students that have scored between 65 to 75. Okay, so what you will say is that 68% of my class has scored between 65 to 75. If he says what is the number of students who have scored between, let's say, 60 to 80. Okay, so you'll say 95% people have scored between 60 to 80. Similarly, if he says what is the number of people who have scored between 55 to, so this is 70, 80, 85. Okay, so you say 99.7% people have. So 99.7, it means out of 40 people, if you take 99.7, so if you take just zero point 0.3 into 100, so this is 41, so 0.12, right? So literally you don't have any person who has scored beyond this range. Okay, so I hope this is clear, right? Krishna, is it clear to you? Stop me if you have any doubts on this. Krishna, do you have any doubts on this? Okay, no doubts. Don't worry, even if you have doubts, we'll revisit this again next week. Okay. So, okay, so this is done. Now Z score, I'll not go into Z score because people had little doubts in this. So we'll revisit this and see it properly next week. Okay. So I'll not go. So these are not very important. Normalized vector is basically the vector divided by its magnitude. Okay, now scaling of the data is very important. So why scaling is important? For example, you're collecting, I'll give you the same example that I gave yesterday. So for example, you're collecting the data of people, and you are saying that depending on the income of that person and the age of that person, I'm going to predict what is the budget of what is the amount, what amount he will spend on his new house. Okay, so you're trying to predict that. So based on his age and his income, you want to predict whether how much amount he'll be willing to spend on his new house, to buy a new house. Okay, so for example, you do a model, and so your range, for example, your income range in the data might be from $20,000 to $1 million or multi-million dollars maybe, and your age will be varying from just 25, let's say, to 60 or 70, or let's say 80 years of age. Okay, so your age variation, I won't say variation, but age magnitude is very small compared to your income, right? Income is going in thousands, 10,000s, lakhs, millions, right? But your age is just tens, right? So when you form a model, and if you don't scale it, your model will always say that age is not important, okay? Because I see the magnitude of your dollars is big, so I don't even, I can easily ignore, the model will say I easily ignore the age, it's so small. A person might be of 25 or 27 or 30, it's nowhere near to, what my dollars are changing, right? Some person is earning to $20,000, some is earning $200,000. So that's where it is very important to scale your data, right? You want to make it unitless. You don't want to make it biased towards units which are huge in number. Okay, so that's why it is very important for everyone to scale the data. It is not necessary to scale data for every model. We'll also come to that, but specifically for linear regression, it is very important to scale the data. Okay, keep this in mind. So you can scale the data with many techniques. So one of the techniques is x minus min. This is called the min max scaling. So whatever data point is there, you take the minimum of all the data. So here minimum is 1, and then you subtract that data point with the minimum, and then you take divided by the max and minus min. Okay, so so for example, 1 minus minimum is 0, divided by the max minus min. Max minus min is 5 minus 1, 4. Similarly, you calculate like this. So all the data points will fall between 0 and 1. Okay, so max app scaling is basically similar thing. Just you need to take the absolute value of the maximum amount. So for example, if you have 1 2 3 4 5, so your highest value is 5, you divide all the values there by 5. Okay, otherwise if you have, even if you have minus 5, still your max absolute value will be 5. So again you will divide by 5, and this will be minus 1. Okay, so this range will be between minus 1 to 1. Thresholding is again another form of binary threshold. So it is nothing but you are giving a binary output to the numbers depending on some threshold you have set. For example, if I set the threshold as 3, so whatever we see less than equal to 3, it becomes 0, and whatever if we see greater than 3 becomes 1. Okay, this threshold is a user defined thing. Normally it can be set at mean or a median, so that whatever is above the median is 1 and whatever is below the median is 0. but it can be anything, right? It is a user defined input. Okay. Okay, so I mean, basically, your machine learning or your modeling is divided into these these 5 steps. So you have the data you need to pre-process. Now, pre-processing, we have just learned the scaling part. There are many things in that. So, for example, you could be, cleaning the data. For example, you are converting. First of all, you have to remove the missing values. Most of the uh, data collection might have missing values, and then you may be removing outliers, as we have discussed. Then you might be doing scaling. Okay, so this is the pre-processing step. Then you have a fit the model. So you fit a model, then you check your accuracy, and then you come back. So this is an iterative process. You check your accuracy, then you again do a pre-processing to improve your model. So pre-processing also includes feature engineering. So we'll not get into that right now, but just to have an understanding. So you can introduce more and more features which are more beneficial to the model, and then finally you have a prediction. Okay. So I'll just take a 1 minute break for Krishna to just digest all this. I'll just take a 1 minute pause. Okay. If you have any doubt, just drop on the chat box. Okay, so let's get back to business. Krishna, do you have any doubts? I'll just unmute you, and if you have any doubts, you can ask me.
I'm fine. Thank you, Amish.
Okay, okay, okay. So let's continue. Um, so normally your machine learning will, look like this. You have multiple features. Okay, so this is all we call as X. Okay, you can have any number of features, right? So it can be one, two, and go up to, thousands, millions even. Okay, so this is typically what you call as the X matrix, or the feature matrix. This is a vector, so each row is a vector. So each row is a data point which constitutes of 4 feature vectors. Okay, and this is your statistical series. Okay, so for example, if you want to do a mean median mode, you will not do a mean median mode on this. You'll do a mean median mode on this. Okay, so what is the mean of the data on this feature, or what is the mean of this data on this feature? We'll not do a mean median on this, okay, because these are different features. It will have different values. It doesn't make any sense to take the mean of this. Okay, so that is one thing. So machine learning will not going to go into definitions. We have already seen all these things. We'll just pass from here. Okay. So supervised learning and unsupervised learning, regression is basically when we are trying to predict a number, continuous number. Classification is when we are trying to predict a class. It can be binary class. It could be a multi-class. Okay, class as in, for example, good, bad, better, or high, medium, low, or it could be anything. Even let's say. So you understand the sense, right? Classification, yes, no, or male, female is also a classification problem. Unsupervised learning is basically where you, so I keep on giving this example, which is very easy to understand. You have collected data for, suppose you are sitting on a clinic, in a clinic, you're collecting data for height and weight. Supervised learning means we have noted that what each of those data point, you have noted whether it's a male or a female. So every height and weight has an associated mark to it. So whether it was a male or female. Unsupervised learning is that you have collected data, but you have forgot to mark it whether it was a male or a female. Okay, so that's where clustering. It's not basically so unsupervised learning can be in because of many things, right? So obviously, supervised learning is a better machine learning technique where you can get better insights. Unsupervised learning, you're limited to your business knowledge, or you're limited to whatever understanding you have about the data. But when does this unsupervised learning arise? Because supervised learning, so whenever you're collecting data, there's a cost associated with it. Okay, so many times what happens is, getting the output is not, it's not easy, many times. And many times you have the data, but you had the data in the past, but you never knew what you were looking for. Right now you have realized that, okay, I was looking for this particular output. Okay, so what do you do right now? You don't have any choice, right? Because that data has gone. Yeah, it's a past data. So that's why unsupervised learning comes into picture. So we have discussed this. I think Krishna is also comfortable with this. We have seen all these things last time. Supervised learning, unsupervised learning. So God and the guess, we have also seen this example. Regression is a number, classification list of values. We have seen this. Okay, what is a classification regression? Examples on supervised learning, we have seen this. Clustering, we have seen this. So clustering is basically the groups where you're forming. So, I mean, it is independent of the outputs because you don't know the output at all. So you have 4 groups. Now it's up to the, data collector, or it's up to the person who is seeing the data to, get insights from these. So what we have discussed is supervised learning. The first and foremost, example that one should start with is the regression. Now, regression again, I think Sunil had this doubt today that there are multiple models in machine learning, and why we should start with regression, or why regression. So when the basic answer to this is, when we were seeing that God function and your guess function, you don't know what God is telling that function to be. He could have designed that process to be a linear process. Okay. Now, if you start fitting a non-linear model, you're basically wasting your time, wasting your cost complexity, increasing the cost complexity of your servers. So you're having an extra cost for which you don't need it, right? So it's always better to start with a simple model, see if that model is improving. So I'll show you this live example today, why a simple model is better and why not every time a complex model is to be applied. Okay, so we'll go. So linear regression is basically of output, which is a function of many inputs in the form of a plus bx plus cy plus so you can call this as a plus beta 1 x1 plus beta 2 x2 plus beta 3 x3. This is linear regression. If you have polynomials, so these x can have also powers in them. So x to the power 2 or x to the power 3. And if you have, okay, so that is polynomial regression. Now, what is regularization? Now, today we'll start with regularization, the concept. So I think last Sunday I talked about little bit of overfitting and underfitting. So we have already seen this. It's very easy to understand what is the best line to fit. Then we saw what is the gradient descent. I told you the example of that bowl, and how that drop will move here and there. Okay, so what is the cost function? We have discussed all these things. So we have seen all these things. Okay, so I'll just pass along. Okay, now let's go into the regularization part. Okay, so let's see what is regularization. I'll don't see the hyperparameters. Just concentrate on what I am showing here. This I discussed last Sunday also, but just to have the better essence. Suppose your data is kind of structured like this. Okay, so these are the data points. What is the best model that you can fit with this? So whatever the number of points are there, those number minus 1, that degree of polynomial you can fit. So for example, if there are 3, 6, 9, 12, 15, 16, for example 16 points are there, so you can fit a polynomial of degree 15. Okay, so how it goes like this. I mean, it's difficult to draw, but just understand this essence. It goes like this. So kind of you're fitting a 15-degree polynomial, which touches all the points or goes through all the points. So there's a typical what you call complex bias variance trade-off. Okay, so this is complexity of the model. Okay, what is n here? Sunil, n is the number of data points, not the features. We are talking about just one feature there. We were talking about just one feature, and n is the number of data points. So, okay, I'll try to explain here. So this is a complexity, and this is your error. This is a very important diagram in statistics in machine learning, and we will always try to come back to this diagram always. I mean, whenever we fit a model, understand this. So complexity is basically what is the complexity of the model you're fitting. For example, uh, order 1 polynomial, which is a basic linear regression. Okay, basic linear regression, that is least complex model. You're just fitting a line, right? Then there will be order 2, that can be a parabola, and then there will be cubic. Then there will be quadratic. I mean, not quadratic, to the power 4. Then there will be 5. So as you go on increasing the degree of your polynomial that you're trying to fit, your complexity of the model is increasing. Okay, so this is 1, this is 2, this is 3, this is 4, 5, hence like this. Okay, now there's a concept called training and testing, right? So training error or a testing error. No, now whenever you are fitting the model, right? So you have the data with you. You have fit the model on that data, and then you want to predict for a new data, right? That's your aim, right? You don't want to predict for the existing data. That answer you already have. If it is a supervised learning, you already have that answer, right? It's not what machine learning wants to do. Machine learning wants to predict something which you have all not seen in the past, right? So that is called a test error. Okay, so you're trying to fit a model which you have the error. So whenever you have, let's say, a data points, for example, you have 100 data points, just divide this 100 data points into 80 and 20. That this ratio can be anything, right? This can be 60-40, 50-50, but generally it is 80-20. 80 you use for training and 20 you use for testing. Why? So you fit your model on 80 points and then you test your model on 20 points. Okay, because why you're doing this? Because, for example, when you are a data scientist, you want to give. So, for example, if when your boss asks you to, give a model, you give a model, and then you don't say that, okay, let the new data come, and then we'll see how my model is accurate or not. That's not how you should go, right? You already should have some idea of the accuracy you're giving the model for. So that's why you're doing this. Otherwise, if you say that, already trained my model on 100 data points, there's some error. Okay, now whenever a new data comes, then I'll see what is the accuracy. That's not how you should do. What you should do is, you have 100 data points. No one has told you to use all the 100 data points. You divide the data into 80-20. You use 80 for training and use 20 for testing, so that you have. So when you are training this model on these 80 data points, that model your model has not seen these 20 data points, right? So for in that case, this becomes new data for your model, right? Now, so for example, when you're trying to fit the, you're fitting the model, so there is a cost function associated with it, right? What we are seen that RMSE in linear regression. So we are always trying to minimize this RMSE, right? Now, and I also told you that if I have points like this, and if I fit a line like this going through all the points, my RMSE will be 0. Okay, so basically, and if I have, I draw a single line, then my RMSE will not be 0, but it will be close to 0. That's what we are trying to achieve, right? Now, this line, just see how it goes. If I increase my complexity, this always go to 0. This is a training error, because you have told your model to minimize the RMSE. Now, if you don't keep a constraint on your complexity, you said, I am not bothered whether you fit a line or a quadratic polynomial or a cubic polynomial, just fit it. So your model say, okay, I don't have any issue. I'll fit a line. I mean, I'll fit a curve which goes through all the points. My training error will become 0, right? Now imagine there's some point here you want to predict. Imagine the error you're having in this case. It's huge, right? So for example, if data is uh, your data is something like this, and you have fit a line like this. Now if imagine if there's some point here, this error will be huge, right? This error will be huge. So this is the new data, and this is the test error. So you have fit a model which has train error 0. But when it comes to testing, you are incurring a huge error. That's not what you wanted, right? You wanted something that does fair on all cases, right? So, for example, you draw a line here. So, in that case, your model will be, I mean, that error will be lesser than what it is. So, I'll again draw the complexity curve once again. Oh, sorry. So, let me. So your training error will always become to 0. I mean, it's smooth, not like this. I mean, I'm drawing with the mouse, right? It's a little difficult. So it will always become 0 as you increase the complexity. What about the test error? How it should go? So your test error will, let's say it starts from somewhere here. It'll goes to minimum and then it will start increasing, right? That's what we saw. So as you increase the complexity of the model, your training error will always become 0 at some point of time. But your test error at some point of the point it will become minimum and then it will start increasing. Your objective as a data scientist is to achieve this particular point where your test error is the minimum. Okay, so this is what your objective is. Now, when this is your objective, you can either start from a higher complexity model and then come like this, or you can start with a lower complexity model and go like this. Okay, so that's why what we do, this is kind of foolishness, right? We don't want to, because higher complexity models will have a lot of calculation cost. Your servers will be engaged. You will see when we go into higher, very complex models like support vector machines and all. Those are very you know computationally expensive. Okay, so you don't want to start like this. You start with a linear regression, see what is your test error. If it is okay, you got some value, then you start with a polynomial with second power. You see a third like this, you increase, and then you see that whenever this goes upwards, you stop there. So this is your point where you should stop. Okay, so uh, what you call is a bias variance trade-off. Okay, this is a very important concept. This is the same thing which is underfitting and overfitting. So when my data is like this and I fit a model like this is a very high variance but zero bias. Okay, the model is not biased towards anything, right? It is going to every point. So it is a high variance model. But if you fit a simple linear line, it is biased, right? It doesn't care about any point. Okay, it doesn't go to, I mean, it's not biased, it's high biased. I mean, it it it's not giving any particular importance to every point, right? It is biased. And it is high bias and low bias means, let's say, if, for example, if my model is reaching each of the points, okay, so it has a zero bias. It means it is not giving anyone extra importance other than the other point. It is going to every point. But this model is biased. This model is getting affected by few points, but it is close to some points, but it is not bothering about every point. Okay, so highly biased and low variance. I mean, it is not varying too much, right? It is simply going on its own. It is not varying too much. So this bias variance trade-off is the same thing. So whenever you are increasing the complexity of the model, your variance will increase and your bias will decrease. Okay. So now just drop me on the chat box whether you have understood this concept or not. This is very important, and I think it should be clear to everyone. Just drop me a yes or no. Okay. Okay, great. I think everyone has understood. That's great. Okay. So now regularization. Where does regularization come into picture? We'll see that. What is a regularization model? So I'll go to hyperparameters later. I'll just first let's complete a polynomial regression. So we have seen that order one order one equation is like this. Order two equation is like this. Okay. So I mean, there's nothing much to explain here. Okay, just fitting a linear model here as such, and then we are seeing the. So I think this curve explains what we are trying to establish here. So this is a very high variance, zero bias. This line is a uh, high bias, low variance, and so this is underfitted. We don't want your curve to be like this. Okay, this is very extremely overfitted. I would say this is also overfitted because it is not smooth. You always want a smooth curve, right? So when we'll do splines, we'll see how to fit a very smooth curve. But still, this is better than this condition. So that's how your underfitting and overfitting will. Okay. Now regularization. Now, regularization is a little difficult thing to understand at first, but just bear with me. If you don't understand in one try, we'll again reiterate. So I'll go first to ridge regression. Now, just focus on this part. What is this part? This is basically the RMSE, right? What we were trying to decrease in a normal linear regression. Everyone agrees, right? So this is the RMSE minimum of y minus x of theta square. Okay, so this is in vectors, so that's why this you don't have the sum here. But basically, we are trying to minimize the y actual minus y predicted. So predicted is a function of x and parameters. So this is what RMSE is, what we were trying to reduce in your linear regression. Everyone agrees here. Any doubts on this part? Can I get a yes or no on my chat box? Okay, so it's clear. Now, what I told right now, if you remember, you don't want your training error to drop to zero, right? Because we are saying that I can have, I mean, adjust your model. And for example, if you have betas, beta 1 x1 plus beta 2 x2, there can be certain cases. I i i uh, i mean uh, keep in mind this, not every time, but there can be certain cases where you are trying to reduce this training error to the least possible. Okay, and so he just think theta as beta here. Okay, whatever I write beta, just think that as theta here. Okay, so there can be instances if I increase betas to huge amounts, and you know there can be cases where this is in the bracket, so there can be cases where this becomes very close to zero. It may not become exactly zero every time, but you can have certain instances where you increase the betas to very high values and this becomes zero. So we don't want that, right? What we just discussed is we are trying to have the minimum training error, but your testing error should also not increase, right? So I don't sorry. Okay, no change. Sorry. It's very difficult to draw here. So I don't want, this is your training error, I don't want my testing error to go above, right? So I don't want to reduce the training error to my minimum. I want to achieve this point. Okay, so but I don't know what is this point, right? It's very difficult. If I would have known this point, then machine learning wouldn't have existed, right? Modeling would not be an art then. Just knowing this. So modeling, by the way, is an art, right? So whatever we are discussing here, it is something which has related to your understanding of your basic business, understanding of the process. You just can't have your model decreasing accuracy every time unless you know something about the data. So what we are trying to do here is you're trying to minimize the training error to the least possible point, but not to zero. Because if your training error is zero, it means if you are 100% accurate on your prediction in training, there's a high chance that it will be very bad in your testing. Okay, so what you do, you introduce this term. What it says is, forget lambda. Okay, what it says is, if you increase your thetas too much, okay, to reduce this part, to reduce this part, this part will start increasing, because this is a squared sum of all the betas. So for example, this part is beta 1, oh, beta 1 square plus beta 2 square plus beta 3 square. Okay, so whenever you're trying to reduce, so this is beta, so if you're trying to increase the beta and reduce the RMSE to 0, whenever you're trying to do that, this part will increase, because it's a squared sum of the betas, and then you will not be able to achieve your minimum. So you try your best to reduce this. This will increase. You'll not increase. You will not get your minimum point. So what it means is, the whole thing will be minimum at some point of time where you have got the optimum betas, beyond which if you decrease this will increase. Okay, so you have to achieve a minimum wherein if you increase the betas further, this will decrease but this will increase, and the overall thing will increase. Did you guys get this? Yes or no? Okay, some people are not clear. Okay, can you explain with numbers? No, no, explaining with numbers, because it's difficult to write, and a lot of things need to be seen. Yeah, do you have a conceptual example? We'll see that in the code. Okay, I have the code with that, and we'll see that how the code performs. But just you know think like this. Forget this part. Do you understand this part? First of all, give me a yes or no. Do you understand this part? Okay. So I think everyone understand. Yeah, this is RMSE. Everyone understands this part, right? No issues on this. Now what I told is y minus beta 1 x1 plus beta 2 x2 and so on, whatever number of features. This is your RMSE, right? Sigma of this. Agree? And you're trying to minimize this. So think about the model. Think about the model. The model cannot do anything here, because this is fixed. This is coming from the data. The model cannot do anything here. This is also coming from the data. So as this one. What it can do, this is in the bracket. So minus this, and this is also minus. Okay. What the model can do, increase this very much. Increase this very much. I will somewhere I'll get to 0, right? Because if I keep on increasing this is a minus, this is a minus, and if your y is positive, it'll always tell that have your betas very high, and you'll come to a point where it is 0. Is this clear? Let's take step by step. Is this part clear? Okay, so this is clear to everyone. Now, so you have given your model all the freedom to increase beta. You are saying that go ahead, whatever you do, whatever you want to do with betas, increase it to whatever level you want, and just decrease this. So your model will happily say, okay, no problem, I'll decrease this to 0. No problem. I'll increase this, keep on increasing this, and I'll decrease this to 0. Okay. Now you are very clever. Tell the model, I'm not giving you that freedom. I am saying I'm introducing this term. Okay, let me rub this. I'm introducing this term. As you try to increase your beta and you try to decrease this, I will pull your hair. I'll say, no, I'll not get you to do that. Because as soon, for example, see, If you want examples like, for example, with five, let's say initially it is 5. Okay, now you are saying that your betas will decrease and it will become to, let's say, 1. Now I have introduced this term, so let's say I lambda is 1, and the sum of betas are, you know 4. Okay, so as soon as you decrease this to 1, this becomes 4. So what will be the resultant term? This is 1 plus 4. This is again 5. So your model says, oh my god, I tried to decrease this 5 from 1. I was doing so hard, but this guy has introduced this term, and this has added 4 to my 1, and I again come back to 5. Are you understanding this? So imagine this, initially this was not there. Okay, this is 0. This was 5. Now your model is happily reducing this and it is going to 1. But you are very clever. You are saying that no, I'll not allow you to decrease this to your least possible, because keep this in mind, right? You're not allowing this model to go here. You're trying to constrain somewhere here. Okay. So what you do, you say, okay, you go on decreasing this, your betas will increase and so will this number. So for example, when this has become 1, you start you this value becomes 4. So what is your final number? 1 plus 4, 5, right? So your model says, oh my god, this is a very confusing state. What I'll do, I try to decrease this, but you have added 4 here, so my overall cost function becomes 5. I was 5 there, so you don't let me decrease. So your model will say, okay, no problem, let me decrease this to, 3, and this will be, let's say, 1 at that point of time. So your resultant score function is 4. So your model says, okay, no problem, let us decrease this to 2, and let's say this increases to 1.5. So these are two fighting functions. This will increase, sorry, this will decrease, this will increase. So let's say the decrease here is bigger than the increase here, so you'll get 3.5. Now, as soon as you decrease as 1 and you increase this to 4, you get 5. So, what is the least point? You get 3.5. Okay. So, in this curve where you are going to 1, now you have only reached to 3.5. It means you are closer to your point where your testing error might be minimum. Okay, not 100%, but might be minimum. You have tried your best not to go to the least possible training error. You're somewhere between in the middle, and that's where you are expecting your test error to be minimum. Now, is this clear? Always remember, these are fighting functions. One is increasing, other is decreasing. One is decreasing, other is increasing. That's why there's a trade-off. Okay, so you need to trade off. At what point it's like something like the demand supply, right? If your demand increases, your supply decreases. If your supply decreases, your demand increases. You need to have a equilibrium, right? So that equilibrium is your least point. Okay, so if you know the demand supply curve, how it happens in market, so your demand price and demand changes, so you need to have this equilibrium. This is your overall minimum, right? Because this point, it's not stable. Okay, so this is very important, right? So I've got this thing, then I think our today's session is very successful if you have understood this, because this is very important. So now let's read this. It shrinks the parameters. Therefore, it is mostly used to prevent multicollinearity. Don't get into this term right now. It reduces model complexity by coefficient shrinkage. So what I told as model complexity, the model complexity. Now, when I tried to explain your model complexity, I was talking in terms of powers, right? 1 or 2 or 3 or 4. Your model complexity is also based on your coefficients. If your coefficients are too high, so if your coefficients are too high, your model is very complex, and you end up as a test, end up your training error here. Okay, but your test error will be very high at this point. Okay, so it reduces the model complexity. It reduces the model complexity by coefficient shrinkage. Coefficient shrinkage means it is not allowing the betas to go beyond a certain point. So it uses L2 regularization. L2, why it is saying L2? L2 means the squared. Okay, here if you see, forget this lambda. If you see this theta, this is a square. So when I wrote that this as beta 1 squared plus beta 2 squared, so it is using the squares. Okay, so if this clear, then let's take a 2-minute break. Just understand this, register this in your mind, and then again we'll start. Okay, just take a 2-minute break. Okay, so if you have got this now, I'll ask one question. Okay, okay. Now, before that, this lambda is basically the amount of regularization you want to put. Okay, so as a user or as someone who is modeling the data, you initially you don't know how much regularization you want to put here. Okay, so I mean you don't have any idea what your lambda should be. Should it be 1? It should be 10? What should be 100? Because you don't know how this function is behaving, right? So this is something called as a hyperparameter. Okay, hyperparameters are basically parameters of the model which the user should be feeding in. But how will the user know which is the best hyperparameter? Whether zero point 0.1 is good or 10 is good or 100 is good, how will it know? That's wherein your cross validation will come into picture. Okay, so we'll learn about cross validation today. and how you should tune your hyperparameters based on the cross validation. So it is very important for a person or a modeler to understand that how your lambda should how much lambda you should put. Okay, now a question for you guys. Okay, if you answer this, then I think you have understood this very good. I mean, this crystal clear. I fit a linear regression model and I fit a ridge regression model. But in the ridge regression model, I put this lambda as 0. What will be the output of this linear regression and this ridge regression? Will it be same? Will it be different? Will it be more? Will it be less? Output as in, let's say, RMSE, or the outputs, predictions. What will be the predictions? Sharad, excellent. Both will be same. Excellent, Sharad. So, because as soon as you put this lambda as 0, it's the same thing that you are trying to do in the linear regression, right? So this is the most important thing you need to understand, that this is something what the user is telling. The same thing is happening. Your linear regression, everything is same. You're just inducing something called as a punishment or a regularization in statistical term. I call it as a punishment. You don't want the model to try, not exactly punishment you could say, but yeah, you don't want your model to try extremely hard to reduce your training error. You want to give it some control over it. Okay, so this is your control. Now if you have understood ridge regression, I think there is no particular thing that can stop you from understanding lasso regression. Okay, so lasso is the same thing, is absolutely the same thing. The only difference is it doesn't have a square here. Okay, it has beta 1 plus beta 2 and so on. It doesn't have any square here. Okay, so this is very important to understand. Lasso and ridge, it's the same thing. So just to give your visualization, and this is one of the very important interview questions you could say, or the most important understanding of which learn lasso one can get, and this is one of the most important figures of ridge and lasso. Suppose this is your function of your linear regression. Okay, so this is your optimum point, right? This is your minimum point. Similarly, this is your RMSE for your linear regression. This is the optimum point. Now when you're having a squared betas, your beta, this punishment would look like a circle in ridge, and it will look like a square in lasso, because it doesn't have a degree, right? So these curves are basically linear. Okay, and this is a circle because it has squares in ridge. This is lasso, this is ridge. Okay, in this case, if you see, when this optimum point comes here, there's a chance that these betas can become 0. You see, in this case, your beta 1 is 0. But here, when this optimum point comes, this is what it is saying, that you cannot have a beta anywhere between this. If you go here, I will punish you. So your optimum point is here. But here in this circle, you can never get a beta which is 0. So what this essentially means is, a lasso regression can do a feature selection. For example, if it sees that some of the betas are not influencing the model, it can drop them to 0. Okay, and only keep one feature. But your ridge regression can decrease your B1 to the minimum point, but it cannot become 0. So ridge regression cannot do a feature selection. I think Sunil had a question last day, that how do you understand which are the features which are important. So I told that in a linear regression, the coefficients which are very 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 small, those are those are not required in your model, because those can be ignored. But in a ridge regression, it will say that which of these are 0. I mean, it will say which of these are small, but it will not reject them. lasso will straight away reject them because it knows that this beta is 0, beta 1 is 0. I don't need that beta 1, so it can do a feature selection. So what it has done is essentially that you have two features. Now it is saying that only one feature is important. You have beta 2. You can forget about beta 1. Beta 1 as in the x1 feature, the coefficient of x1, and beta 2 is the coefficient of x2. Okay. Now if this is clear, now let's move on to your Python notebook. Okay, Sunil, I think he has a question here. Sunil, I think I'll unmute you and you can ask the question on this. Just yes, Sunil, you can ask your question now. Sunil, go ahead. You ask your question.
Oh, sorry, I was also mute on from my side.
Okay.
Okay. So on the first, you told if that is rectangle, B1 can be 0, but B1 can be 0. But in the second case, larger regression, B1 can't be 0. Why it's so? In this circle, we can see B1 can also go to 0, 0, and it can be 0 also, isn't it?
No, there's a very little chance, having this intersection. So this is a smooth curve, right?
Oh,
So this is a smooth curve,
yeah. This is,
and it
okay.
and don't think that this will intersect here. There is no space. As soon as it touches here, the tangents touch here, it's over. You cannot go beyond this.
Oh,
Okay, so this is just a visualization.
yeah.
Okay,
Yeah, got it. Basically, those circles, three circles where those are touching, that is you are discussing. Am I right?
Yeah. That is
Okay.
point where you're, but your zero is on this axis, right? So your function, sometimes it can be like this, where your circle and this meets here, but that is very, because what will happen, it will cross through the circle inside, and this area is not under your purview. So that's why your function will always be restricted outside. So it's a mathematical, just this is some kind of a visualization. Don't delve into that too much, because it's mathematical squares and there is a differentiation involved. So that's why I'll not go into depth, but just know this: a lasso regression can do a feature selection. A ridge regression cannot do a feature selection. Okay. Okay. Now I'll.
Okay, got it. Thank you.
Okay, no problem. I'll put on mute. Okay. Now let's go to our Python notebook. So today, Vasant, I think you had this query of, let's have some data set that we can work on. Start also, I think I have incorporated that today, and we'll start with. Let me first read up this drawing. Okay, so okay, now just type in these codes as you do. So as you type in, I'll just explain each of the lines here. Okay. sklearn.datasets. sklearn, we knew what is this. This is a scikit-learn. This is a package where all the machine learning models are built in. So yesterday we saw that how easily a single line of code, did all the calculations. So sklearn is very powerful. So all the model concepts and all the model calculations lies there. Okay. Now from sklearn.datasets. So sklearn.datasets means sklearn has some inbuilt datasets inside it. Okay, so Python users have loaded some inbuilt datasets in the sklearn library, so you can access those. So sklearn.datasets import the load Boston. So load Boston is the name of the dataset. Okay, you don't need to load this one right now. This is another dataset. Okay, import pandas as PD. Pandas is the library for your data frames. Now your load Boston is basically a function. You use that function to call in you store that function in your, basically your data set, in your whatever name you want to store it. So Boston has two components. One is the data and one is the target. So data is basically the features, and the target is basically the um, your y. or your prediction. Then what you do from sklearn, import linear model. Okay, this is the same thing what we saw yesterday. Reg-R is equal to linear model dot linear regression. It's basically storing the linear regression model in reg-R. Then reg-R dot fit xy. Okay, you just fit your xy here. Okay, now don't execute this. Put this under commands. Okay, you can do this, but just to visualize this, how your data frame looks like, I've made that into the data frame. So just put these under commands. Okay, so I'll just put it here. Okay, now pd.dataframe is some command we already know that it is trying to establish whatever insight it is as a data frame. So what it is saying is convert the following data into a data frame. The data is Boston. So Boston.data, there are two ways you can access the components of a data frame, either this or Boston data. So the data will come here, and columns is the Boston.feature names. So this is typically of so any data set what you load from your Boston data set will have these two components, data and feature names. Okay, and then you put the price as your Boston target. Okay, now let's see as the Boston data set. I think we have it here. Okay, so first let us see what it has. So basically then we are printing df.head. What is df.head? Df.head means just print the first 5 lines of this data frame. Okay, so it has printed the first 5 lines. So there are how many features? See, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and this is the target. All good till here. Now see what each of the features mean. CRIM is the per capita crime rate. So basically, you want to predict the price of the house, okay, in a particular locality. So we have collected a lot of data on various attributes, and now we are going to see what all attributes are there. So crime is the per capita crime rate of the town. Zn is the proportion of residential land zoned for lots over 25,000 square feet. Basically, how your residents look like. I mean, resident places looks like. Indus is the proportion of non-retail businesses acres per town. Charles River dummy variable. This is one if track counts river, zero otherwise. So if a river flows, something like that, right? NOx is the nitric oxide concentration in that locality, average number of rooms, age, proportion of owner-occupied units built prior to 1940. What is the average age there of the units? What is the weighted distance to 5 Boston employment centers? And top employment centers, what is the weight distance? So these are basically features. You don't want to go into the depth of each of the descriptions. So the same data set we have. Now what you do is, now see this. This is very important. You have this whole data set. Now, right now, I have just told you to take this out as 100, and next to 20 points we'll use to test. But you can do 80-20 ratio. Okay, we'll see that later how we can randomly choose 80-20 ratio. So it is always better to choose this randomly. Um, I mean, don't ever choose the data frame as top 20, I mean, first 100 or first 150 or first 200. Don't choose like that. I mean, first 80 proportion. Don't choose like that. For example, if there are 500 points, don't choose the first 400 as the training net and the next 100 as the test set. Any ideas why? Can anyone answer this question? Why you should not choose the first 100 just like that, or first 80% just like that? Okay, I'll answer this question. So for example, you never know when the data was collected and what was happening. Krishna, is sorted data, not sorted data exactly. you never know how the data was collected, right? I mean, maybe the top 100 data points were collected during the day. There was, for example, if you are collecting for height and weight, so first, or let's say the if you have collected the data points on a day, in a day, and you have taken the first 100 data points, which were supposedly in the morning. So I think you could say that, I mean, if for example, if it is you started your data collection from 11 a.m. in the morning, and you took the first 100 data, so people visiting a clinic at 11, from 11 a.m. to, let's say, 2 p.m. will be females, right? Most of them. I mean, because males would have gone to offices. I mean, I'm not stereotyping. I'm just giving you an example. Okay, so it can be anything. So you never know what had happened during that point of time, or the first 100 or first 80%. It's always good to take your data, randomly, do a random selection from your data points. And Krishna, you could also be right saying that, if your data is sorted, you'll get always those particular elements and not. So for example, if you're directly taking it from your database, then there's a high chance that the data is sorted on the basis of keys, primary keys, or whatever, names, anything it can be, right? So you might not get all the information in the data. So it's always better to do a random selection. But for illustrative purposes, I have kept it simple for you guys right now. So what you're trying to do is you're trying to do a your training set. You're trying to train. So what it's saying, take the first 100 elements from the data frame and take the 0 to 30. 0 to 30 means take all the features, and don't and your similarly take all the y's corresponding to these elements. Y is the basically the 13th column. Okay, I guess there's no problem in this. Then you do an X test. X test is basically the X that you want your model to predict on. Okay, so X test is doing a selection of the next 20 points, and now you are fitting the model on your train, and then you are predicting on your test. Okay, and then this is your actual. So actual you already had, right, because it is a supervised learning. So actual also you take. Now what you do is you take out this sklearn matrix import mean squared error from math. Math is again a library which has all the functions. RMSE is what we told, square root of the mean square error of actual minus predicted, right? Print the RMS, print the coefficients. See, the RMSE is 1.588. So this is the RMSE on your test data set, and these are the coefficients. So your equation will be like minus 3.4 into crime plus 5.3, this is 10 to the power minus 3 into Zn plus minus 1.68 to the power into 10 to the power minus 1 into this. This is how your equation will look like, and this is your RMS. Okay, agree? Everyone agrees here? No problem at all till now. Very simple. You don't need to run it right now. Just if you have any doubts, what is number 13? Okay, 13 is basically so let's count it from Python. Okay, in Python sense, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 13 is the number of columns of this data. Yeah, so just see this. If you remember our first Python class, what we told, if you do like this, then it will start from 0, but it will not take the 13th column. It will take till 12. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. These are the features of your data frame, and this is your output. So output is the 13th column according to Python, and till 12th are the features, right? So basically, when you're when you're fitting a model, if you would have seen this yesterday, regression.fit or xy. So your x and y need to be separated. You don't want your y to go into the feature, right? Then you're not predicting anything. You're using y to predict y. Okay. So your x should be independent of y, and then there should be a y here. Okay, so that's why we are taking the separating the column 13 and the features. Is this clear? Okay, so you have seen this, right? Now let's do the same example in ridge and lasso. You do a scalar import linear model. You take linear model dot ridge alpha is equal to zero point 0.2. Okay, now what I've just intentionally put it 0.2, but you really need to test your data, do a cross validation, and then get to the point of what should be your lambda. We'll see that what how we go there. Okay, okay. So this is basically you're fitting your model again here. This is you're printing your coefficient, and then you're printing the RMS. Now see this. This is very important. When you did a simple linear regression model, your coefficient was your RMSE was 1.588. But when you are decreasing the complexity of the model, it need not necessarily always improve your accuracy. This is 1.88. So RMSE higher. Now this is a test RMSE, right? This is not the training RMSE I'm talking about. I'm testing the RMSE on the prediction and the actuals. Prediction which I've done on the next 20 points, not on the already trained data. So this is the actual prediction what we are talking about. So this is the test RMC. So this it need not be necessary always that you're decreasing the complexity of the model decreases RMSE. It means the ideal model would have been linear regression. So when we were seeing this diagram, so might be there's a point. Okay. For example, linear regression has fitted the model at this point, right? Maybe there is a little more complexity that we need to achieve this point. Now you're decreasing the complexity, it means your testing error is greater, right? So that's why modeling is an art. It is need not be necessary that always a little less complex model or a more complex model will give you better. So that's why it is always advisable to start with less complexity, start with a ridge lasso, and then go into the uh, you know uh, linear regression. But why do people don't do this? Because if you do a ridge or a lasso, you could start with anything. There's no particular saying that lasso should be used or ridge should be used. Ridge and lasso almost behave similarly, as we saw. But if you want to do a feature selection, you see that your features are too much, I don't want so many features, then you could use a lasso. But having said that, sorry, uh, having said that, this alpha I have fixed, right? There can be certain instances where your alpha, uh, making your alpha, increasing your alpha betters your RMC. There can be certain instances where increasing the alpha decreases your RMC, or sorry, increases your RMC. So now when you're doing a hyperparameter check, as we saw that hyperparameters are uh, designed by the model, designed by the user based on the cross validation. So an alpha of very less, for example, if I do it here, if I put at very little alpha, then you see your RMSE is almost going to your simple linear regression RMSE. Where is this? 1.588, and this is 1.88, almost going to that point. So it is always advisable to keep this alpha from 0 to 1, so that, or 0 to 10, or 0 to 100, whatever you want, so that you can include that normal linear regression also in this. So if this would have been the minimum, your cross validation will tell that you should set alpha 0.0001. Alpha is that lambda, what we were saying, that punishment, right? That punishment we were seeing in this one. This is alpha. This is actually lambda here, but in Python it takes as alpha. Okay. So if I keep this very low, this is the same linear regression, right? So always it is better to start with 0 to 100 and then let the model decide which is the minimum point. Now, if you see, if I increase this to 100, this RMSE is increasing. It means it I am decreasing the complexity of the model, but I am increasing the test RMSE. It means my model is better suited for linear regression and maybe for further complexity, but I should not decrease the complexity. Okay. Now, did you guys get this? Is this clear? You want to code it yourself? You want to take 2-3 minutes time and code it yourself? We can do that. Otherwise, we can proceed with the next topic. Okay. Sunil asked for 2-3 minutes to understand. Sure, Sunil. I'll unmute you guys so that you can ask your questions without typing in. Okay, I've unmuted. So if you guys have any questions on this, you can ask me.
I coded the first part, but I'm getting a syntax error on the df print df dot head in the bracket. It says invalid syntax.
Did you follow the same thing? Print df dot head?
Yeah, that's what I did. Print and then space df dot head in braces. Just give me syntax error, invalid syntax.
Okay, just remove the braces there.
Okay. Missing parenthesis, yeah, giving again syntax error. Oh, I think I need to give some bracket outside also. I think it's a different version. That's the reason we are facing this. Yeah, it's running fine now.
Fine.
I need to give one more braces. Yeah.
Okay, could you go on 97?
97. Okay. Yeah.
I mean after the screenshot, because in 96 just we are collecting the data and also predicted value Y we have taken.
Yeah.
So yeah, is that 82? Sorry for that. So now we are on 82. We are saying okay, now we need RMS.
Correct.
Means whatever theta 1, theta 2 we have got, based on that we have already x1, x2. Based on that, whatever the actual and predicted, give me root mean square. So finally, we are getting root mean square value.
Correct.
Am I right?
Correct.
And our main intention is that to get RMS as low as possible.
Perfect. Yes.
Okay, so we are getting the coefficient here. So we have got 1.5. Now we are giving another try with 100 in 97.
Yeah. Now we are going another model called which.
Yeah, we are just changing the value of alpha.
Yes.
Basically.
Yeah.
Yeah. Okay. We are giving 100, and with that we have got 3.222. So our root mean square is increasing in this case. What does this mean for us?
Okay.
Now our line is not fully fitted, means lesser fitted now comparative, because
yes.
our RMS has decreased.
Yes. So
if we compare,
yeah.
Sorry, just give me 1 minute. So if we compare only these two value of alpha 0 versus 100, then we can say 0 is better for us.
Correct.
Okay, so just you have tried, go for 95 once again. 95.
Sorry.
Could you go down? Yeah. So with 95, how much we are getting? Okay, just we are giving different try. 95.95 is
in the bottom one, I have used lasso, and in the top 97 I used ridge.
Oh, okay. Lead versus lasso you have used.
Yeah.
Okay. So now the least value which you have got, that is 1 point something.
Yeah, 1.5.
So what does this mean? Yeah. So what does this mean? We have to put alpha randomly something, or
Okay.
it will detect itself.
No. So that's what we were saying here, that to find alpha, you need to do something called as a cross validation, okay, and a grid search. We will go to that point in today's class. What is cross validation? What is key-fold cross validation? And on that basis, the model will choose the optimum alpha.
Okay. Means my question is that this is a random alpha we are giving, and we also don't know what should be the right alpha.
Correct.
So the model will itself detect what is the alpha value, or we have to randomly pass on.
No, that's what I'm saying. The model will not detect the alpha directly. We have to do something called as cross validation, and based on that cross validation will tell the model that this should be your alpha, optimum alpha.
Okay, okay. And again, that will be package, or we have to write code for that.
We'll get to that.
Means we are in.
We'll get to.
Okay.
Yeah.
Okay. Oh, that's great.
I have a quick question. So if we put a loop between 0 and 1, right, for alpha.
Yeah, that's the I was telling you.
Hello?
Yeah. So yeah, absolutely. That is the point. If you put a loop between alpha between 1 to 100, you'll get your various values of RMSE, and then you'll get the lowest RMSE
Minimum.
accordingly to you. So that essentially is what cross validation will lead to. So that's what I'm saying that. So for example, right now I am just testing on a particular part. Okay, so just 101 to 120, right? But as I've told you, this is a this is a particular set. Cross validation will ensure that this alpha is minimized all over the data set, not just this particular part. So what you're telling this absolutely right. You basically need to check for different values of alpha, what is the minimum point we are achieving, but on what data set you want to achieve, right? On does it only mean that you should attain on these 20 points, or you should go beyond that? That's why I'm saying cross validation. We'll do a cross validation there, and then we'll do a grid search. What you're saying, that running a loop between 1 to 100 or 1 to 1000, whatever you want to specify, that is called a grid search. Okay, so based on your cross validation and a grid search, the model will tell that this is your optimum alpha. Okay.
Okay, and one more question. In which case we will use reach, and in which case large? So,
Okay, so that I think right now I explained that your lasso, whenever you're saying that you have too many features. Okay, so for example, you have, let's say, 1,000 features in a model, right? You cannot go on predicting with 1,000 features, right? It will create a lot of noise in your model. So whenever you want to see that, okay, these 1,000 features, I want to drop some of them. I don't want use a lasso. But if you have, let's say, 5 or 6 features or 10 features, then use a ridge. I mean, it doesn't really make any difference so much. It's just that lasso can eliminate a variable based on the importance of it. Ridge cannot eliminate a variable based on its importance.
okay, got it. Thank you.
Yeah.
So, yeah, this is Krishna. A quick question. The lasso model, right? You're telling it will eliminate the future, right? Based on some algorithm, right?
Eliminate
So,
the feature. Yeah, feature.
yes. So, but in a practical case, right? Future might not the value of the future might not be great, but it might influence the model, right?
No. So, for example, if your feature coefficient is very small, okay, I mean,
Okay.
there's something called an importance. So, for example, when we see a normal distribution like next week properly, we'll see basically how your feature importance is taken care of. But having said that, so for example, if your feature is too less and your variance of that feature is very low, it means that feature. I mean, don't forget this variance part. Just think like this: if your feature is very low, close to zero, it means that feature is not affecting anything. So when we are saying a linear regression model is equal to y, is y equal to a plus beta 1 x1 plus beta 2 x2, And beta 2 essentially means that if I change one unit of x, what is the change in what is the change in y? So if your beta 2 is 2 less, for example, it is 0.000001, one unit change in x will change, I mean, one unit change in x2 will change 0.0001 unit of y because of beta 2, then you can as well remove that beta 2. It is not adding any value to your model. That's where your feature selection comes into picture. Now we will see how exactly you do a feature selection based on your, there's a distribution involved. You cannot just see if it is less and you just eliminate it. You need to also see the variance of that or the standard error of that, what you call in statistics. But for right now, till now, whatever knowledge we have, just think like this: if the magnitude is too less to impact why you should keep it. If you're 1,000 features, out of 1,000 features, you're feeding in so much of data, and out of those 1,000 features, you know 600 of them are not important. Why you need to carry all that excess baggage with you, right? So that's why lasso becomes important that in that sense.
No, but my question is, see, one model prediction is fine, right? But when you go to practical application, that particular feature might have a bigger influence on the data, right?
No. So how do you say that in practical sense? I mean, your data is saying that statistically this this feature is not important, right? It is. That's why you're fitting this model, right? If you would have known that this practical feature, I mean, practically this feature is important, then you might as well not fit the model, and then your model will not lie itself. I mean, if you really know that this is actually important, or
Okay.
then your model will not lie. It will say that statistically, yes, this is important. You need to keep that feature. But
Oh, okay.
there are certain cases, there's something, your statistically, your mod, I mean, basically think like this. If uh, your data is changing all throughout, but in your one feature is constant almost everywhere, it means that feature is not important. Your y is changing, but that feature is almost constant everywhere, right? So then it means statistically that feature is not important. Whatever value you give, okay, or take the vice versa.
No,
You
yeah,
have,
yeah. See,
yeah,
one example I will give you from my industry, right?
yeah,
Uh, the year the house is built, right? That is something which basically determines what kind of construction code it has gone through. That to be put in that. But the variation of the year is less, right? Say if I take a state of Texas or something like that, the variation of the year is say between 1950 to 2000, for example, I'm giving.
correct.
So the variation is less when you compare to the other parameters, right? So the model will think, okay, this is not a good future to consider, right? But in an industrial practical this thing, it's an important parameter to consider. I'm just giving an example, right? I might
So
not be correct.
what you said that your variation is less. So if your variation is too less, I mean, first of all, the thing that we call that you need to do a scaling and all that. So that scaling will somehow take care of the magnitude of that model compared to others. The other part is that if your variation is actually very less, when you're collecting the data, it's because you have not collected the data before that. Okay, so you have particularly collected that data on that particular frame, so there's an error in the data collection, or there's a constraint in data collection, because you have not collected data for let's say 90, or even if the data wouldn't have existed, right? So that is not something what you can do about it. But that's where your statistics also becomes constrained, right? So your data model will always be as good as your model will always be as good as your data. If you don't, so for example, if you only say that I have collected the data for this year, for example, I'm just taking an example. So, for example, I just take, let's say, I want to say that whether a lung, smoking leads to lung cancer or not. So, for example, if I just take data of 1 year, there will be many things, and I wouldn't able to say that so many years have contributed to cancer, right? So, I mean, that's my fault that I don't have that amount of data, right? But if I collect data for, let's say, 10 years, then I can say that, okay, for example, if a person smokes for, let's say, 4 years or 5 years, then I can tell, that feature is important. But if I take for just 1 year, then obviously that time period will not be important. But that is not the fault of the model, because we have not given the model to experience different data points, right? So your question is very valid. I understand that some of the parameters, there are constraints where you don't even have the data, or you don't have make business sense out of it. But if you don't have that variation in that particular feature, the model will reject. I mean, the model can't help, because it doesn't see the variation. It doesn't. But think like this also, right? There are certain cases where it actually is a. I mean, this particular case you are saying, this might be an example, but there are 90 other examples wherein that excess feature is adding to noise. That model, that feature is not varying too much, but it is adding noise into the model and hence decreasing the accuracy. Okay, so that's where that's where your feature selection and feature engineering comes into picture, and that's why we say modeling is an art, not a science exactly. So you need to have some background data, knowledge about the data and all.
Yeah, that I totally agree. So, but the question I have is there a way to tell? Okay, I know that this particular feature is important. So, is there a way I can tell the model, okay, consider this, don't drop it?
Yeah. So, if you, for example, in Lasso, particularly, you can't do that. Okay, because Lasso will consider whatever statistically is not valid, it will straight away reject it. But when you go into more complex models like trees, there's a plot wherein these are the features that are important. These are the features which are noise. So on that basis, you select on your own. It doesn't drop it immediately. So it will just tell you that these are the features that are statistically important, and these are not. These are the features not important. But then it is up to you to reject those or accept those. That is up to the user. But in Lasso, you cannot do that. Lasso will straight away, it will reject whatever it is significant, statistically insignificant.
Okay, that makes sense.
Yeah.
Okay.
Yeah, what do you mean by noise in this last show?
Okay. Noise is something like you have a feature that is not actually helping in your prediction, but it is ruining your prediction. So, for example,
Okay.
last time I discussed, right, whether your ice cream sales are being affected by the shark attacks, right? Now you have you have collected data, and you are seeing that your ice cream sales are affecting the number of, shark attacks, right? Ice cream sales is a noise to your data. If you are trying to predict whether your shark attacks have increased, ice cream sales have nothing to do with it, right? It is basically a noise to your. It's an added feature that you have collected, but it does not add any value. It might have a correlation. That is something else. It might or might not have a correlation. But having said that, there are certain cases where they absolutely don't add any importance to the model.
Okay, good. Thank you.
Yeah. So any questions on this? Okay, let's take a 2-minute break.
So one question: are you going to provide this code also as part of this?
Yes,
Okay.
I think in the slides by default it will be.
No. These are my codes. I've created my own. So these are not in the slide, but I'll send them. Not a problem.
Yeah. Okay.
Okay. Let's take a 2-minute break and let's continue after that. Okay, so I think let's continue. Okay, now first we'll do the cross validation. Okay. Okay, now I've been telling a lot about cross validation, and hence we'll first look at cross validation and how it is very, very important to have this into the system. Now, we all know that our goal is to pick the best model, right? But what is the best model? We never don't know, right? So there is a big constraint on that. So there are two things that you can do on this, right? First, you need to decide on a model, whether you want to go into a linear model or you want to go into a non-linear model, whether you want to do a polynomial regression, whether you do want to do a support vector machine or a k-nearest number. I mean, first of all, the model, which model needs to be applied? That is a question. Some point you have, sometimes you have this business knowledge that you know that this is a linear relation, so you know that this linear model will do the best. Sometimes you don't have absolutely any idea what relation it could be. So then basically you do a hit and trial. But whenever you're doing a hit and trial, you need some metrics, right, to understand whether you're going in the correct direction or not, right? How do you understand that? So as we have discussed till now, that you have a train and a test set. Now, the biggest problem with this condition is how do you divide that train and test? Whether you take the first 100 point, whether you take a random 80 sample, whether you take, or random 60 sample, it's a big question of what proportion or what data you need to take, right? That's a big question. So that's where your key fold cross validation comes into picture. Now understand this. K is something that the user is inputting, right? So basically K fold means K parts. Suppose your K is equal to 5. Okay. Now what it essentially means is divide your data into 5 parts. Okay. So for example, if there are 100 data points, divide it in 20, 20, 20. Okay. Now what you do is take the first 420s and test it on the last 20. You do this. Then take the second, third, fourth, fifth 20, test it on the first 20. Okay. Then take the third, fourth, fifth, second, uh, third, fourth, fifth, and first 20 and test it on the second. Similarly, you do all for all the 5 parts. So there will be 5 iterations, right? If there are k folds, there will be k iterations. Whatever RMSEs you get for each of the folds, just average it. Okay, so it ensures that you don't give any biased or biasness to any part of the data. You don't have you don't take the last part of the data, you don't take the middle part of the data, you take all parts of the data, test it on all essentially all parts of the data and take an average. Now this partition is based on the based on a user input. You can take 10 parts, you can take 5 parts, you can take 8 parts. Generally it is 5. I mean, that is the better what you call thumb rule, to use 5. Most of the people, data scientists, use 5 as the fold. But sometimes even if it is huge, then you can do on a 10 part data. And if you have computationally, so it means each model has to run 5 times, right, on 5 parts of data. So it becomes computationally very expensive. Now if your k is 10, then your model has to run 10 times. So now if you have 10 models you want to test, and then each of the model has, 2 3 parameters. You imagine how much time it is going to take to fit a single get into a particular solution for a particular data. So that's why generally it is used as 5, not more than that, but you can use it as you want. So I think this is very clear. You divide the data into 4 parts and test it on one. Then you take the other part and the other into training, like this, so that each of the data has seen the other tests, and then you average it. Okay, so this is just an example. Don't go into the details. Just understand that these are the different scores of accuracy, and then you take the average. Scores dot mean, you take the average. So this is your average accuracy that your model should give. Okay, okay. So now now that you have understood this, let's go into nearest neighbor classification. So we'll last 15 minutes we'll introduce to you to Kaggle. What is Kaggle basically, and let's have a taste on that. But before that, we'll go into nearest neighbor. I'll not do the coding today because it will be too much for you guys to digest in one day. So many models, but let's understand the basics so that next class we can start with the recap of this. And uh, could we be? I didn't understand, Sunil, what you're trying to say. You want to go back to the K, uh, K-fold cross validation. You have any questions on this? Okay, I'll unmute you. Okay, just a sec. Yes, Sunil, tell.
Yeah.
Yeah.
Yeah. So basically, we have 100 data. We have divided 20, 20, 20. So you mean every train is for 20 or 100 data?
Sorry, I didn't get you. What
Okay.
did you want to ask?
Okay. So the left one, that is the 100 data.
This 100,
What
100 is
about?
just an example. This can be anything, right?
No, that's fine. Yeah, that's fine.
Hmm.
So first one is 100 data. The second one is 100. Out of those 100, you are taking first 20. Am I right?
Yeah. So first 20 is for the test, and the rest 80 is for the train. Then first 20 and 40 to 100 is for train. 20 to 40 is for test. Then first to 40 is train, and then 60 to 100 is test. 40 to 60 is for test. Sorry, 1 to
Okay.
40 and then 60 to
Yeah, that's fine.
yeah.
So we are doing the same. Last one is take 1 to 80 and 80 to 100. That is for test.
Correct.
So we have this time we have done and we have taken the RMS average of this one.
RMC average for all those 5 iterations. So
All these 5.
this one will give you an RMSE. This one will give an RMSE. This will give you RMSE. Like this, you'll get 5 RMSE,
So,
and then you take an average.
yeah, 5 RMS we have got. We have taken the average.
Yeah.
So what does this mean for us? Earlier it was 3.2.
Uh-huh.
This is coming 2 or 4. What does this mean? Which one is correct? This one or that one? Is our intention was that to minimize the RMS.
Hmm. Okay. Now, the question that I think you guys had, that how do you optimize the hyperparameter? So that's why I wanted to go to K nearest neighbor so that you get the complete picture of what you're trying to do. But for example, you have alpha, right? Now you're trying to
Yeah, that was the main issue. Yeah.
trying to optimize the alpha. Now, for example, for you have started a loop. Okay, for alpha equal to 1, you have fit 5 models and take the RMSE. Alpha equal to 2, you fit 5 models, take the RMSE average. Alpha equal to 3, take the RMSE average. So each alpha will have one average RMSE, and then based on that average RMSE, you need to understand which is the best alpha. So the test, this validation, k-fold cross validation, doesn't have anything to do with your
Alpha.
alpha. Yeah, this is basically the testing part to improve your testing. I don't want to test on a particular data set. I want to overall test it, right? I want to get an average of everything. I don't want to test
Yeah.
on biased data. I don't want to test it. So this is the testing efficiency,
So
bettering your testing, not your. It has nothing to do with the alpha. So each alpha will have 5 iterations, and then take the average. Each alpha will, so alpha one will have a average RMC, alpha two will have a average RMC, and like that.
so still the problem is same. The problem we have divided in 5 parts, but problem is same. We need to find out the alpha for which RMS is as minimum as we can make.
Correct. Now,
So are we going for a loop, or is there? Oh, sorry, please go ahead.
yeah. Okay, we'll go there. How to do a grid search? We'll go there. Don't worry. Don't hurry up to go into the final solution.
No. Basically, I was thinking that K neighbor problem, K neighbor algorithm you are started describing. So is that related with this one again?
Yeah. It will be. So
As like,
how to
okay,
optimize the hyperparameters? So in K nearest neighbors, K is a hyperparameter, right? So just
okay,
understand at this point of time. Initially, let me draw and explain you here. Initially, what you were doing, you were not doing all these things. You were just doing data train test, right? You were getting some RMSE, and then on the basis of that, you were taking a decision. Now to improve that testing part, you are just doing this. You have done nothing to your alpha right now. Just to not have a
correct.
biased test, you are doing a 5-fold test. Okay.
Okay, yeah,
Okay.
sure.
Okay. So now let's go back to nearest neighbors. Okay. Now what essentially nearest neighbor is basically very simple, and it just refers to uh, the very popular saying is that while your children go to school, and then you always say that always mix up with guys who are good. You will be you inculcate all the behaviors of the people who are close to you. So if you're in a group in which people are not so good, you'll kind of land up like that. If you're a group in a group in which people are extremely good in studies, they are good in extracurricular activities, so you tend to compete with them, and then eventually you uh, you know uh, go to that level. So it's you are as good as your group. So this is a very popular thing that people tell their teenagers when they're going to school, go to school. So essentially, nearest neighbors is exactly the same idea. So in nearest neighbor, what you're doing is it is a very important, could say a very important model, because it is testing on the fly. It does not have a model prepared prior to your test. So for example, in linear regression, we already had a model. We had that equation in place. Now, whenever your test comes, we just apply that equation on the test data and then get a prediction, right? But nearest neighbor is little different. It doesn't have any equation as such. Whenever it sees a new data, it will start calculating from there. So for example, let me draw here. For example, this is your training set. Okay. So you have say for example, you have a data for legs, number of legs, whether it has feathers, whether it can swim or not. Based on that, whether you have, classified the eggs into chicken, I don't know what is this, ducks, swans, and something like that. So whenever a new thing comes up, it has some number of legs, some number of, I mean, whether it has feathers or not, whether uh, it can swim or not. So you just basically check the distance. Now, distance in terms of numeric, whenever you say the legs, I can understand. How do you understand whether what is the difference between yes or no, right? So we'll come to that. We'll come to that later. But just to understand, whenever you have numbers in the data, so whatever this test is computing as a distance, I mean, how far is this test data set from the trained data set? from each of these categories. So for example, you calculate the distance from a swan. Distance, will understand what is the distance. Just understand this first, that you basically are computing the distance measure between this particular test set between the categories which are present in your train data. So you say, for example, this distance has come to let's say 2. This is, let's say, 5. This is, let's say, 4. This is, let's say, 7, and this is, let's say, 6. Okay. So what is the least distance between the test set and the training set? This is 2. So basically classify this as a duck. Okay. Now, if this is clear, then how do you say what is a distance? I mean, what essentially does a distance mean? So let us do in numbers. Okay. So for example, there's a person called A, and I just have two features. Okay, income and age. Both are numbers. So let's say his income is X, his age is Y. There's another person B whose income is P and age is Q. Okay, simple. So what you're trying to do here is basically create what is the distance between A and B. So distance between A and B is called the Euclidean distance, or X minus P whole square plus Y minus Q whole square. So what is the distance? So as we said, these are vectors, right? If you remember, each row is a vector. And how do you calculate the distance into vectors? You take the distance between each of the features, x minus p whole square. Always whenever you are taking a distance, it has to be square, because you don't want, like in RMSE we were doing a square, in standard deviation or variance we are calculating a square. Essentially you don't want to keep negative values. So x minus p whole square plus y minus q whole square, this is the distance between A and B. So if you have a third feature, that minus this whole square gets added here. Another feature and gets added here. So that is how your distance measure is calculated. Is this clear? I mean, just the distance measure. Is this clear? Give me a yes or no. Okay, I think it's clear. Okay, so I think this is good. So then, if you have got the understanding of the distance, then okay. Now, what it nearest neighbor says. So, for example, I get as we had shown here. Here, my closest distance was 2, and then I don't remember the exact numbers I put. So whenever you are calculating this test distance with all the classes, okay, first you'll do a sorting. So 2, 4, 5, and then based on that k, if it is classes, you will take a majority voting. So you say, okay, at my distance, which is the least, it is a duck. At my distance 4, it is a duck. At my distance 5, it is a swan. So when I have k equal to 3, these are the top three distance categories from my test. Now I take a majority voting. It says the duck is, I mean, this 2 of the 3 times I say it's a duck, that's why it is a duck. Okay. If you have k equal to 5, then again you take 2, 4, 5, and then 6 as a hen. Okay, so on. But this is, I don't know what is this. This is, let's say, baby chicken. The baby chicken is at a distance 11. However, if you take a majority voting, it is again a duck, right? Now, since you're taking a majority voting, it is always advisable to take k as odd so that you don't have a tie. But now, how to decide how many numbers you need to take? I mean, how many k's you need to keep for your testing? That is, so k becomes a hyperparameter for nearest neighbor. The model will not tell you. As a user, you have to do a cross validation and a grid search so that you can understand what the value of k is. Okay. I don't think there's any issue on this. It's a very simple topic. So just let's see the slides. So basically, this is a majority vote. Okay. And if it is in numbers, then you take the average. Okay. So you have two classes, green and brown. You get a new data set. You see the distance of this from, let's say, all the points first, and then do a sorting. And then you take the distance. So this is one distance, this is two distance. So k equal to 1, which is the closest point, this is brown. But interestingly, k equal to, sorry, k equal to 3, it gives this one, it gives this one, and gives this one. So it is a green. Okay. Now, this is kind of difficult how you need to, you see the result is completely changing if you change k. So that's why finding k is very important in this method, and that's where the cross validation and the grid search will come into picture. Okay. K-nearest neighbor is not very widely used precisely because of the fact that whenever your new data comes, it's called a lazy learning approach. Okay, so lazy learning means that it is always trying to form the model when the test data comes into picture. Now imagine if you are, in real businesses where the test data is so fast, how much time it will consume to calculate a particular data point, a distance from each of the data points that had existed, and then find the output. So it's a big computationally expensive feature, when a computationally expensive mechanism, and then it is doing on the fly. So it is taking much more time. So it's always, trying to calculate after your test data comes, then it is doing a sorting, then it is selecting. So it's something that people don't want, right? I want the prediction right away. I don't want to wait for you to do so many things, and then if there are, let's say, 1 lakh data points, is going to calculate 1 lakh distances and then do a sort, which is also a computationally expensive thing. Then it will show me the results. So it's very slow, in fact. So nearest neighbor method is not very used too much in actual, real life problems. But it is good to know. Sometimes you might require this part. So I think I have explained all the things here. So basically, your K becomes very important whenever you're doing this, right? So your definition of K is very important. Okay, we'll see Voronoi diagram next time. Don't get into that right now. So you have understood what is the distance measure, and this weight factors and all. We'll do that. I mean, in the next class. I'm just giving an overview of nearest because, anyways, we'll do a recap of this next time. So I think this is what we want to do. Now, we have seen this cross validation and then optimizing the hyperparameter. What it is doing is basically, so there is some kind of error for each of the, so for example, if you see the codes here, so every time it is calculating the scores on the basis of, for example, it has calculated the score on the basis of n equal to 1. Now it has calculated the score on the basis of n equal to 5. You see, there's a significant improvement over the accuracy. Okay. Now in classification, how you accuracy you measure the accuracy is basically there's a simple thing. If it matches, then you count it. If it doesn't match, it you don't count it, right? So it means here 93% of the data, I mean 93% of the times it is matching. Uh, not ni- I think where is my cursor? Okay, yeah. Um, so this is actually 93% times it matching, and it is 100% matching for this. So basically, this is means 96% times it is matching. Okay, so basically what you're doing, this is a segregated view what it has been given. You are basically running a loop for k equal to 1. It's always odd, so 1, 3, 5, 7. Let's say you go up to 101, something like that, and then you see what is the mean score and take the maximum of that. Okay, so okay, now as we have discussed that what is the complexity in case of nearest neighbors. So k equal to 1 and k equal to 100. Which is more complex? Is k equal to 1 more complex or k equal to 101 more complex? Can you answer this question? Okay, I'll give you a hint. Which is more, trying to overfit? Sunil says k equal to 100 more complex. Any more answers? Sharad says 100. Okay, not exactly like that. So a k equal to 1, imagine this. K equal to 1, every point is trying to, you know, give special importance to a point which is just neighbor to it. It is not seeing 100 points around it. It's just seeing one point. It is too much trying to overfit, right? It is not taking a overall picture. It's not seeing an overall picture like what we had done, right, in linear regression. It is not seeing an overall picture. It is trying to fit whatever it sees. Similarly here, it is trying to fit whatever it is very close. I just take whatever is closer to mine. I just take whatever is closer to this. So if this point is closer, I just take this. So k equal to 1 is a very complex model. I mean, it is trying to very overfit. So for example, if you go to your Voronoi diagram previously, this Voronoi diagram will be too much lines will be there. So these are the basically boundaries. So anything that falls within this boundary is classified this. Anything that falls in this boundary this classified this. Now imagine if my k equal to 1, I put these boundaries will be much smaller, right? So very small boundaries will be there. And that's why it will try to overfit. But if it is k equal to 100, it is seeing all the 100 points around it and then taking an average. It is not taking a action very hastily, or it is not trying to overfit. It is not trying to overfit. It is not trying to fit every point. It is taking some generalization. Some generalization. It is taking a majority voting over 100 points, and that's where it is voting. Okay. Okay. So now we have 5 minutes left for today's session. Okay. Now I will just show you what is Kaggle. So Kaggle is basically okay. Let me plot this. Kaggle is basically a website where you can, practice or compete on various machine learning uh, problems, which are posted by companies or posted by most of them are posted by companies. So you can, see this. I already have an account here that has directly logged me into this. So basically, when you go into the Kaggle, it will open your profile. Then you need to log in and use you can use your uh, Facebook profile to connect, or you can use your email. So the basic kind of whatever Facebook or something you have, it's similar to that. So these are the competitions that I think, yeah, these are the competitions you have entered. So the competition where I went to Paris, and these are the kernels that you uploaded. This is a discussion you have taken part into, and then these are the data sets that you have uploaded. So I don't do much of Kaggle because I do different competitions, but these are the competitions that are, you know, these are the entered competitions. These are the active competitions you can go into. So anything you want to. So these are the prize monies that the top team gets. But you know, you can enter this competition, and then gives you the description. If you want to join the competition, you just click here, and then there will be the data. Here you will find the data. Here you will find the kernels where people have posted their codes for whatever they have used, you know, in the model. And then this is a discussion where people, you know, discuss whatever they feel like. And this is the leaderboard, who is leading and who is, you know, lagging. And these are the basic tools. So nothing much here. You can just log in here. So it's kind of a Facebook, but only difference is that it deals with data science. A lot of things you can, you know, also look at how what people are discussing right now, and it's just good to have you know, account in here. Okay, so I think we have another 2 minutes. I'll just open the forum for questions. And if you have any questions, you can ask me. Otherwise, we can close.
So, Sudeep, I have a question basically.
Yeah.
So, are we done for finding the answer for that? I mean, data which we are looking for, house prices in Boston. Means
No,
we
no,
were not able to find. We are not able to. That's not finished. Okay.
that's not fair.
So, because at this stage we are looking for to find the correct value of alpha. For that, we moved on k-never problem, where we are finding the k, which is not very clear, but next time we will repeat again, you told. So once we will find the value of k, 1 or 100, then what next?
Okay, now don't confuse all the things together. Okay, what you have learned today is a regression problem, and then bridge problem, and a lasso problem. Then you have seen that you can do a cross validation to use your uh, testing efficiency, increase your testing efficiency, and then calculate your alpha. Okay, we have not done that calculating the alpha. We have not done that, but that is what we
Okay.
proposed. K nearest neighbor is a different model. It is not nothing has it has nothing to do with your linear regression. K nearest neighbor is a model, completely different model. It has nothing to do with regression. It has nothing to do with
Okay. You mean as like lasso or reach, that is another model basically.
exactly. It's a model for prediction. That's what I was saying. No? That your test data comes in, there's you make a prediction. So K nearest neighbor is another model. So we'll go into that depth next time. But for now, just understand K-nearest neighbor is a new model that we have seen. And so everything will not be a regression form, right? So we will see 15 models in this course, or 15. I mean, I don't
Okay.
remember the number. So the K-nearest neighbor is another model, and Ridge and Lasso is another model. Now, K-fold cross validation. Don't confuse the two things. K-fold cross validation is what we see, that 20-20 part, k is equal to 5. That is something to deal with your testing, increase your testing efficiency. That is another concept. So keep these things separate. You have learned ridge lasso, you have learned k nearest neighbor, and then you have also seen what is k-fold cross validation, which is trying to improve your efficiency of testing. Okay.
Okay. Okay, got it. Means that is a separate part basically.
Yeah. Yeah.
So I just have it correlated. So in which case you will go for k-never problem? In which
We'll
case
see that. We'll see that.
ledger entry.
Don't
Okay.
jump the gun right now. We will see that eventually. What cases we should go for nearest neighbor? What cases we because we have so many models to learn, right? I cannot tell you which model right now you should go. As I told you, we are not God, right? We don't know which model is the best. You have to explore all the models, or whatever models you are learning. You have to explore everything. That's where your data science becomes an art. You cannot, you know, tell that, okay, this is the data. I think I will fit k-nearest neighbor, and it'll be over. No, it cannot be like that. You have to take multiple iterations, do multiple modeling exercise, and get the best part. But as you go on with your experience, you start to know that this kind of data is good with this model, this kind of data is good with this model. That will come to later. And as you go into more depth, you will understand when to use what. But right now, you have not learned that. You don't know when to use what.
Okay, that's great. So as like in lesser ratio, we are finding the minimum RMS. In the same way, what is our intention in k-neighbor problem?
Correct.
Minimize?
Yes.
Because there is no RMS.
No, right now what I gave you an example is a classification example, right? But if you're doing again a regression example, so that's what I'm saying. We'll go into depth into nearest neighbor next time. But again, a regression problem is measured by RMSE. A classification problem is measured by accuracy. Okay,
Got
so
it.
yeah, we'll have the RMSE in k nearest neighbor also. Okay.
Okay. Yeah.
Okay.
So one last question. Sorry for that.
Yeah. No problem.
So assuming that Boston house prices, I have to decide, and I have decided that I have to use regression for assume for timing we can assume.
Uh-huh.
So our intention is to minimize RMS, but we don't know the value of alpha.
Correct.
So what will be our next step in that? In that process.
So your next step, you have already answered the question, right? You don't know alpha, that's why you need to find alpha. So first you find alpha, then you see the RMSE, and then if you are not satisfied with the RMSE, then you move on to a more complex model.
Okay, means will I use the loop to find different alpha, or is there some other module for that?
You have to use the
or
loop.
some other?
You have to use the loop to find alpha.
Okay, and that alpha value can be minimum to max. What can be the value?
That you have
that
to
I have
put,
to decide, or
that you have to put according to the computational expense you can. I can, because alpha can be any value, right? So you cannot put 0 to infinity. That will take forever to compute, right? You need to put some value, for example, 0 to 1000 or 0 to 100 with some bins. So for example, 0, it tests for 0, then test for 0.5, then test for 1, then test for 1.5, something like that. You cannot, because it's a continuous value, right? If you put 0 to 1000 and you don't put anything, the model will not understand which value to take, right? Because it's a continuous number. Okay.
yeah, because I also don't know the minimum and maximum for alpha.
Yeah.
That
So
is the issue.
minimum is 0, maximum can be anything.
Okay, minimum is 0.
Yeah.
Okay, that's great. So Subhadeep, can you upload today or tomorrow that this slide video and examples which you have shown us?
Correct.
Because that is very important for us.
Sure. So I'll send you the slides, the code, and the video. The code itself has the data set.
Okay, yeah.
Okay. Okay, guys. Then we'll close if no one has any other question. Any other question you have, guys? Krishna, Sharad, Vasant. Okay. So I think we can close for today. Thank you, guys, for joining. And let's meet next week with more models and more machine learning. Okay. Bye. Take care.
Okay. Thank you, Shobhit.
Okay.
No problem. Good night.